So looking here, figuring out what is the most reactive, least reactive. So for this first set, what would be the most reactive? Go ahead. Radium. Yes. Yes. Radium would be the most reactive. So for the first one, you would say A. Now, why is it all right, what are we doing? Let's get our phones up. Okay, so for first question on the phone, if you're going to put A. Now, the reason why it's most reactive, remember the trend for reactivities, metal reactivity, is you go towards the bottom left of the periodic table. In other words, go towards francium. Now, all of these elements are in the same group. So whenever you're within a group, the further down you go, the more reactive the metal gets. In other words, the bigger the metal is, the more reactive it is. Okay? The reason for that is the bigger the metal atom, the easier it is to pick off those outside valence electrons. Okay, so then what would be the least reactive, with all that in mind? Yeah, good. What do you think? Yeah, good. Yeah, good. C, good. Magnesium. Yep, so least reactive, they would be higher up on the group. So magnesium is higher up, so it's going to be the least reactive. Okay, so for number 2, you got to put C. All right, now they give us a new list of elements here. So which of these would be the most reactive? It's raising our hand. Yeah. Potassium, good. So that would be B. Now the trend for if you were to a good thing to do when you're doing these problems is utilize the whiteboard markers and the lamination. Mark the elements on your periodic table. Then you can kind of see the trend pretty easily. So if you were to do that, you would see potassium is the furthest to the left. So as you go from left to right, metal reactivity actually decreases. So the further you are to the left, if you're in group 1, like potassium is, you're going to be the most reactive. Okay, so then what's going to be the least reactive? Let's get those hands up. What's the least reactive? Yep.
It's Li.
Li?
C.
Oh, this one's interesting.
Don't shoot me down.
Oh, this one's kind of wild. I didn't realize they have us going this way, and then going up. And then we have GA. Not LI. Nope, not LI. Yeah, go for it. GA, good. So letter A, GA. So if going to the bottom left is most reactive, gallium, GA, that's going to be further towards the right. Now, okay, so now what people are confused because you're like, what? But LI is higher, right? Is that the?
No. I'm gonna ask. So more to the left is more reactive, more to the right is less reactive?
Less reactive.
To the right?
To the right is less reactive. It's kind of backwards.
So it's in K,
right?
So every single time we want to find this perspective count.
Yeah, see where they are comparatively. Now, guys. Now, this one was kind of interesting because they combined going up and to the side. So gallium, even though gallium is lower than lithium, because it's way more to the right, it being to the right more than counteracts it being lower. That makes sense. In other words, you got to look at the balance there. It's not just a matter of, some of these is not as simple as, oh, it's further to the right, or it's going to be up or down. They might combine them. Okay, we got those down? First 4 in the formative? Okay, so then quietly if you haven't already, get your notes to, we're doing periodic trends. So get yourself to the periodic trend slide. Okay, so we learned about one of the periodic trends last class, and that was metal reactivity. So today we're going to learn about all the other periodic trends. So go ahead and get yourself to that page in the notes. First slide here, you got some notes. Yes. All right, so the idea of periodic trends is how can we look at the periodic table and find certain patterns. One of the first things I need you to understand is a reminder of the period. Remember the periods we said you write from left to right, and at the end of a sentence you put a period. Another thing to understand is energy levels. Each time you go down a period, you add an energy level. And I've told you that before. Really all the slides should be a reminder. So like if you look at lithium or hydrogen, for example, it has just one ring there because it's in the first period, just one energy level. Lithium is in the second period. That's why it has two rings or two energy levels, and so on. So francium is in the seventh period. It would have all the way up to 7 rings or 7 energy levels. Okay? So again, hopefully that should be some kind of a review. All right. Now then, review of valence electrons. Remember the group number? That tells you the number of valence electrons. Now, group number, assuming you don't count the transition metals, or the inner transition metals. Meaning, group 1, they all have 1 valence electron. Alkaline earth metals, or group 2 elements, they have 2 valence electrons. Then skip over the transition metals. Transition metals and the inner transition metals, they're weird. They can have different numbers of valence electrons, so there's no real pattern to them. We'll talk more about how you approach those later on in the year, but just skip over those. Then once you get to group 13, also called group 3 because it has 3 valence electrons, and then all the way over to where the noble gases are, where we call those the group 18 elements, also called group 8 because they have 8 valence electrons. Okay, so really, really important slide. This is one of those slides you got to understand. And we're really going to build up on this throughout the year. You got to understand, and the helpful thing is you don't have to memorize this. It's really just, it's written right there for you on the chart. You got to be able to interpret that. Okay, knowing the number of valence electrons atoms. The reason atoms behave the way they behave has to do with the number of valence electrons they have. Okay, all right. Now then, this slide here summarizes all the periodic trends. Okay, so I'm gonna go over it real quick, and then we'll go into specific detail on all of them. First one is atomic radius. Now, atomic radius has the same trend as metal reactivity. Go ahead and add an arrow for metal reactivity. That way, because this is a good reference slide. So metal reactivity, what we learned last class, that has the same trend as atomic radius. Say like maybe MR for metal reactivity. Atomic radius is the size of the atom. Like in your geometry class, what was the radius?
It gives half a circle.
What was the radius?
Oh, it's like the center point to like the outside.
To the outer part of the circle, yeah. So the atomic radius, atoms are, we said they are spherically shaped. So atoms have a radius. So the measure of the radius would be the atomic radius. Meaning, as you go towards the bottom left, atoms get bigger and bigger and bigger. And that actually should make some sense, right? Because remember, we organize a periodic table by atomic number. It would make sense that the radius of an atom that has 119 protons, atomic number of 119, that atom should be bigger, have a bigger radius than one that has only 11 protons. Okay. Now then, electronegativity and ionization energy. We learned about those last class. I didn't really get into the trends of where they're at, but the trend is towards the top right. Now, I did tell you that nonmetals have, which one was that? Nonmetals have high or low electronegativity and ionization. Remember I told you, remember it? Nope. High. Remember I said nonmetals are gases and gases are high in the air. Metals are solid, they're low on the ground. So this trend is actually saying that, right? We said that nonmetals are towards the top right of the periodic table, right? That's why as you approach fluorine, the electronegativity and the ionization energy all go up. Remember electronegativity, that's how badly the elements want electrons. Ionization energy, that's the energy it takes to remove an electron. All right, so as I said, this is a summary slide, but let's go over, yeah, this slide is just there just to remind you of the metal reactivity. Yeah, we went over last. Okay, yeah, it's not your notes. Okay, yeah, but I basically went over this on this slide, so we'll move past that. Okay, so yeah, reviewing ionization energy and electronegativity. So again, metals do not want electrons. Metals freely give away their electrons. So we got a new slide here, guys. Metals freely give away their electrons because that is the most efficient way for metals to get a full valence shell of electrons. Metals are the most stable by giving up their electrons. That's their strategy to get a full valence electron shell. Okay? And that's why metals are going to have a low ionization energy and low electronegativity. Now, nonmetals, they're going to have a high ionization energy, high electronegativity, because nonmetals have the opposite strategy. Nonmetals want to gain electrons because that will be their best strategy to get a full valence electron shell. I'll have a slide kind of explain that a little bit more later. But because nonmetals really want electrons, that's why they have a high ionization energy. That's why if you want to remove an electron from a nonmetal, you have to put in a lot of energy to do so. Okay? All right. So yeah, try and understand, well, why exactly do, as you go towards the top right, why does the electronegativity get stronger? It is basically the exact opposite story of what I told you for metals and them having low electronegativity. So let's look at the Bohr model. Well, let me back up. I want to circle this bullet point for you again. I had you do that at the last class. You have to understand that all atoms are stable when they have a full outside shell of electrons. I'm going to say it again because it is so important. Atoms are stable when they are full, just like you. Atoms are stable when they have a full outside, meaning valence, shell of electrons, okay? So, if you are lithium, you're a metal, what is lithium's best strategy to get a full outside shell of electrons? You remember from last class? Yep, go ahead. You take one off, right? To get a full second shell, you need 8 electrons, right? So lithium could gain 7 electrons, or you think outside the box, it could just lose 1, then it has a full first shell. Yeah?
So what's like the most unstable element?
Oh, the most unstable element, it'd be either fluorine or francium. The ones that are in. But then if you get into radioactivity, you know, it'd be probably one of the actinoids. So it depends what you mean by unstable.
But they're both like non-metal, right?
Francium's a metal. All right, other question? Yeah.
How do they gain and lose electrons?
Well, losing electrons is pretty easy. It's just like the answer to that is really the same. Another atom will want, so if you're lithium, an atom like fluorine that wants 1 more electron. So let me actually answer that question by jumping to fluorine. If you're fluorine needs to gain 1 more electron, then it has a full valence electron shell. So fluorine really wants to take that electron from lithium. So lithium is able to get rid of electrons by pairing up with like a nonmetal that wants to gain electrons. So nonmetals gain electrons by taking them from metals. So in other words, typically metals and nonmetals are paired up together because like opposites attract. Their strategies kind of benefit each other. So again, fluorine wants electrons. It's a nonmetal. Fluorine to the top right. That's why it has a high electronegativity. Lithium, or anything in group 1, has low electronegativity because they actually want to lose electrons to be stable. So again, the point here is this is trying to explain why you go from left to right. So lithium and fluorine are in the same row, same period. That's why electronegativity goes up. Does that make some sense? You don't have to memorize this trend. You can just understand it. All right, moving on. Now, trying to understand, well, why does electronegativity decrease as you go down the periodic table? Well, if we look at lithium, lithium is higher up in a group. Lithium is a smaller atom. And if you compare that to potassium, potassium is a higher up atom. really this explanation is what I gave you last class trying to explain metal reactivity. I said potassium was more reactive than lithium because potassium is a bigger atom. This bigger atom, the positive pull of the nucleus, it can't pull as well on that outside electron as well as the nucleus of lithium can, because lithium's valence electron is closer to its nucleus. Yep.
So this might be a little unrelated, but like the bigger the atom, does that mean like you know how they like split the atom into very small? So with like the bigger the atom, the more catastrophic.
That's getting off topic. I don't want to get into that. Okay, so hang with me here, because to understand this, you got to keep a couple things together. So the bigger the atom, the harder it is for the nucleus to pull electrons towards itself, right? The bigger the atom, another thing that happens is these other electrons basically distract it. Some of you in the back of the classroom understand this, right? Like, let's say one of you's got your hand up, and I start working back there, and then one of you raises their hand, and I'm like, and I feel like I got to answer their questions, and then it takes me a while to get back to you. That's what's going on with potassium. Potassium wants to pull on this electron. Potassium would like to pull on other electrons. It could. Same with other bigger atoms. But the issue is these other electrons shield it and block it from pulling on other electrons. Whereas if you're a smaller atom, there's fewer electrons to distract the nucleus or prevent the nucleus from pulling on electrons. Okay. Questions about that? All right. Now, ionization energy. So ionization energy, that's the energy it takes to remove an electron. So if we look at ionization energy, it increases from left to right. So as we go to the right on the periodic table, it takes more and more energy to remove those valence electrons. Now, the reason why we've already talked about. I said lithium, it's all the way to the left. Lithium is a metal. It doesn't want its electrons. So it doesn't take a whole lot of energy to remove lithium's valence electrons. Whereas if you look at fluorine, fluorine just needs one more valence electron, then it's going to be completely safe. So if you're fluorine, you are highly motivated to hold on to your electrons. It would take a high asking price, a high amount of energy, to remove one of fluorine's electrons. You still good on notes over here? Almost there? Yeah. Good. All right, now then, looking at ionization energy, I said as you go down a group, ionization energy decreases. And that's really for the same reason for the left and right. As you go down a group, the atom gets bigger and bigger. The bigger the atom, the harder it is for the nucleus to pull on its electrons. The more distracted the nucleus will get from those other electrons that will, they say shielding, shields it from pulling on electrons. So that's why it is easier then to pick off. Imagine you're like a raider. It'd be easier to like pick off this one valence electron because the nucleus is distracted by all these other electrons. Whereas if you're a smaller atom like lithium, lithium has a whole lot less distractions, so it's going to be a lot harder to remove that outer valence electron. Okay. So again, smaller the atom, higher ionization energy. That's why as you get to fluorine, fluorine's a pretty small atom, fluorine's going to have a really high ionization energy. I know it's kind of maybe some deep thinking for a Friday, but is what it is, you know?
The more like higher it is, the more like electromagnetic whatever it is, and then the more iron.
Got it. All right, now looking at atomic radius. So, and I've already kind of has said this. All right, guys, you got any select? So make sure you're sticking with me. Atomic radius. So, as I said, as you go towards the bottom left, that is going to be the bigger atom. Interestingly, they can determine like the radius of two atoms by like basically if they shoot X-rays at an atom, it'll bounce off the nucleus. So they can basically bounce the X-rays off two atoms, the radius of two atoms, and then if you divide by two, that tells you the radius of one atom. Anyways, the point is, as you go towards the bottom left, as you go down a group, you add energy levels, atoms get bigger, and as you go to the right, atoms actually get smaller. I'll explain why that is on the next slide. Are we good on this slide? Okay. So getting into and really sort of reviewing, why do atoms get bigger as you go down a group? Why do atoms get bigger as you go down a group? That is, again, because you're adding energy levels. And then there's also what I said earlier, this idea of the shielding of these other electrons. The nucleus, the more electrons there are in the atom, the more these electrons will shield the pull from those protons. So the harder it is as you add new rings, as you add new electron levels, the harder it is for that atom to become shrunk by the nucleus pulling in the electrons. Okay? You take a really small atom like lithium, that nucleus has a really strong pull and there's less electrons to shield it from pulling on them, so that atom's going to be nice and small. Okay? All right. Now then, last one. Why is, as you go from left to right, why do atoms get smaller? Now this one is not obvious. If I were to ask you, hey, sodium has a mass of 23, right? Average atomic mass of 23. Argon has an average atomic mass of 40. Which atom would have a bigger radius? I would assume most of you would say the one with the bigger mass, right? Things with more mass tend to have, they're bigger, right? This is the opposite. Okay, so really key, it's not intuitive. Now the reason for that is, as you go from left to right, so if I were to like draw the Bohr model of sodium, sodium has 3 energy levels, okay? Chlorine also has 3 energy levels. Okay? Now, who has more protons, chlorine or sodium? The chlorine, right? Chlorine has atomic number of 17. It would have 17 protons. Sodium has an atomic number of 11. It has 11 protons. So the nucleus is trying to pull on those electrons. So which of those atoms, chlorine or sodium, is going to have a stronger pull? The pull is coming from the protons. Protons are doing the pulling. So who's going to pull more, chlorine or sodium? It's going to be chlorine, right? Because chlorine has more protons than sodium, so it can pull those electrons closer to itself. That's why chlorine is smaller than sodium. Sodium can't pull as well as chlorine, so it's not going to be as it won't be as small as chlorine will be. Okay? Say it one more time. Chlorine is smaller because it has more protons and the same number of energy levels, so it can shrink its energy levels more than sodium. Okay. All right, almost there. We got one more slide. 2 more slides. Really, just one more slide. Last topic for this is diatomic elements. And I mentioned this when we went over the halogens, but diatomic, di means 2. When we went over the halogens, I said that the halogens don't exist in nature in their elemental form. The halogens always are going to exist paired up with another atom. And I said the reason for that was like because they are so reactive. So I need you to memorize the diatomic elements. So I have them in red there. Now, it's actually not as bad as you might think because I told you the halogens, they always are going to be diatomic. So if you can remember that, all the halogens are diatomic. Then oxygen, nitrogen, and hydrogen. Okay, those are the diatomic elements, meaning they exist paired up with another atom. And I got a couple mnemonics you can use to remember this. So my personal favorite is this. I have no bright or clever friends. All my friends are a bunch of idiots. I'm just kidding. But at least I have friends, though. Right? Anyways, there's some other ones up there. Brinklehoff. Mr. Ecker has this elaborate story about he has this fake cat named Brinklehoff, but like he doesn't tell anybody it's fake. You know, I don't know. But anyways, the bold ones, those are the abbreviations for the elements. Okay. All right. So yeah, you got the formative. We're out of here at 9:19. Just do the best you can with it. I might adjust the percentage that I need you to get on it. But let's just start working on it and see where we get to. I'm going to leave it on this slide because here is your summary slide. So summary slide will be right here. All right, let me know if you got questions.